grade 12. We are now finally at question 9. This is the last question of the question paper. However, we still have to do a video on question 1. Okay, question 1 is going to be the last one because it relates all the topics. Okay, now question 9 is about KC. There is a lot of problems with learners about KC. However, it's not that difficult. Okay, now this question saying the following reversible reaction. Now reversible reaction is one of the conditions for equilibrium to happen. Reversible reaction is one of the conditions for equilibrium to happen. Otherwise, equilibrium cannot happen. The reaction must be reversible and the container or the system must be closed. Those are the conditions for equilibrium to happen. First of all, the reaction must be reversible. In other words, must go forward and backward, and the system must be closed. So we have this reaction. It's a hypothetical one of a gas X, a solid A, and the product will be a X3. Okay, now the graph below show how the equilibrium constant Kc changes with temperature. And now we see something here. The Kc is decreasing. Remember that if the Kc decreases, then you forming or you having more reactants than product. In this case, because the Kc is decreasing, that means that you are getting decreasing as temperature increases. Nah? When temperatures get greater, the Kc decreasing. Now that means that then you are forming more of the reactants, and therefore the reaction is shifted towards the left. The reverse reaction is favored as you increase in temperature. The graph is as you increase temperature, equilibrium Kc decreases. Later on, there's a question about that. Okay. Now 9.1. When 0.6 moles of H2 and excess of A are initially sealed in a container, the system reaches equilibrium at 300 Kelvin. The concentration of AX3 at equilibrium is found to be 0.1 mole per decimeter cubic. Calculate the volume of the container. Now, before we go on, let's record very small things. We're not going to be spending long time here. But first, Kc. How do we calculate the Kc? This is the concentration of product. Concentration of product divided by the concentration of reactants. Remember, the square bracket means concentration. All right, so it's concentration of product divided by the concentration of reactant. So in this specific and something important, solids and liquids you don't include there, no? So no, I'm going to write here, no solids and liquids. This is only for aqueous solutions as well as for gases. Okay, so now let's write the Kc expression for this specific equation. All right, so we have in the product we have AX3. So the Kc for this expression is equal to concentration of product, which is AX3. Now, important, the subscript at the front, these coefficients at the front, not subscript, the coefficients are going to be used to the power. So this will be AX3, concentration of AX3 at equilibrium. This is at equilibrium. It's not everywhere, only at equilibrium, the concentrations at equilibrium. So this is to the power 2. Where is that 2 coming from? The 2 is the coefficient at the front, the ones we use for ratio. Alright, now divided by the concentration of the reactants at equilibrium. However, remember, you do not include the solid. This one is solid, so you do not include the solid. Will be the concentration of the X2, which is a gas. Okay, so will be concentration divided by the concentration, square bracket, of X2 to the power no, not 2, to the power 3. You see the coefficient at the front is to the power, there you can see it, to the power 3. Now this is the Kc expression for this specific calculation, and As easy as this, you will get 1 mark if you write that expression, even if you don't do any calculation. So please, everyone can write that expression. Concentration of the product divided by the concentration of the reactant. You can see where those small numbers coming from is the coefficients at the front. Is the one we use for ratio. There you go, the 3 and the 2. You do not include the solid. Right? No for this calculation. So that is the first thing I wanted to record. Second important thing, they asked to determine the volume of the question say calculate the volume of the container. Now, I'm working with gases. Okay. Now, how do you calculate the volume? They give you the concentration. Concentration is equal to number of mole divided by volume. All right. If we are at equilibrium, then the number of mole is at equilibrium. All right. So this number of mole will be the number of mole at equilibrium. So these are very important things. We are going to use this formula. Obvious, they're looking for volume, and that is the only formula that we have with volume. Okay. Now, here we are going to use the so-called rice table. Okay. Now the rice table. Now, what does R stand for? This is for ratio. Okay, that is a ratio. In this case, the ratios are, what are we going to use is x2 and ax3. Not this one because it's solid. Again, I remember it's not, or record, no that one because it's solid. So the ratios are 3:2. Okay. I stand for initial. Now, initial could be in grams, could be in mole, could be in decimeter cubic, or even could be in grams per decimeter cubic. Could be any of those. It does not matter. It depends on the question. What are they giving you at the beginning of the reaction? In what is the quantity they use in mass? Then you use grams, or in number of moles, then you use moles. Okay. Now this is change. Change. How much that the initial amount changes. Okay. And this is equilibrium. The amount at equilibrium. So if we're starting with gram, then this one will be in grams. If we're starting with mole, this one will be in mole. If we're starting with volume, then this will be in decimeter cubic, and so on. Okay, it depends what you're starting with. And then you will have the final one, which is also E. Final one will be E for concentration at equilibrium. This is important because this is the one that you are going to substitute in the Kc expression. Okay, so let's now start by doing the table. Let's first of all write the reaction here on top so we can see it. So it's 3x2, let's write the unit, the state, gas plus 2a solid, reversible reaction with 2ax3 gas. Okay, let's take all this quickly and move it a little bit there. Let's move it a little bit there. All right, so that is the reaction. Now let's start with our table. R, remember, for ratio. All right. Now, no, let's move this one a little bit to the end because we need the space to do everything. Okay. So we are there. Now, ratio. Now the ratios are 3:2. That is what we have. This one, no, because it is solid. Okay. Now the second Second part of the table is the I for initial. Initial and obvious, we have to go back to the equation. Okay. Now the question says when 0,46 mole of X2 mole, they starting with number of mole, and excess of A are initially seated in a container, the system reach equilibrium. So the initial that we have is in mole. I'm going to write here mole, not to get confused, and the amount is 0,46 of this reactant. What will be the initial amount of AX3? 0. You don't have any amount at the beginning. You don't have product. You're starting with 0 product. All right. So the amount of product at the beginning, initial, is 0. Let's go to C for change. Change. It will also be in mole. All right. Now we don't have change. It's not given to us. So let's go on reading. We don't have any change. This is the concentration of AX3 at equilibrium is found to be 0,1. So they give you the concentration. Now, what is coming after change? Equilibrium. E for equilibrium, however, it must also be in mole. It must also be in mole. We don't have any data. We have equilibrium. Equilibrium in mole per decimeter cubic. What is that? That is the concentration equal to number of mole divided by volume. We're going to use that formula. And then what we have, let's probably do a small line here and another one somewhere there, so we know the table. Right, that is what we have now. The equilibrium they give us the concentration. It is found that the concentration of AX3 at equilibrium is 0,1 mole per decimeter cubic. I'm not going to write the unit because the unit is right here, 0,1 mole per decimeter cubic. Now let's start by completing this expression. Okay, now using this formula, now we're going backward. This is what we have. We have to start completing the table. Using this formula here, you can calculate the number of mole at equilibrium right here. All right. Now, how do we calculate the number of mole? Number of mole is equal to concentration multiplied by volume. All right. So here will be, I'm going to write it. Number of mole is equal to concentration multiplied by volume. What is the concentration at equilibrium? 0,1. What is the volume? We don't know. I'm going to write V. 0,1 V. At equilibrium, you see, number of mole at equilibrium is equal to concentration at equilibrium multiplied by volume. Right? Now, we're starting with 0. We have at equilibrium 0,1 V for volume. How much did this one change? It changed that amount, 0,1 V. Let's go again. You're starting with 0. You don't have any. At the end, you have 0,1 V. How much did it change? It changed 0,1 V. All right. Now, something important here at a change is when you can use the ratio. So here you are going to use the ratio. All right. So now the ratio, we're going to go down here. Ratio is 3:2. 3:2. If the change is 0,1 V, how much will be here? This is very, very easy. Ratio is 3:2. If the change, and this is only by the change ratio at change, so you know we're working there. 0,1 V, then how much we were there? How you do this one? This one is cross product. This is a simple math, but let's do it. This is 2x equal to 3 that multiply 0,1 V. Okay, 0,1 V. So what is that going to be? You have X is equal to 3 times 0,1 1V divided by 2. So X is going to be equal to, let's use the calculator, 3. Okay, we go to the calculator, we were saying, so it is 0,1, let's go back here, it's 0,1 times 3 divided by 2. Zero comma 1.5. So we have here 0,15 V. This is the change for the reactant here. So this is 0,15 V. How did I get the 0,15 V? By using the ratio. Here is the ratio. Ratio is 3:2, is given at the beginning of the table, and you're going to use, you can only use ratio at the change. You cannot use it at the initial, you cannot use it at equilibrium. You can only use it at the change. So 3:2, that means that 0,3 V is going to be converted into 0,15. Here is how to use the ratio. Okay, so now what is the change? Let's go to another color here. Let's use the green. All right, now what is going to be the equilibrium? What is going to be the amount of equilibrium? Well, will be the initial minus the change. So here will be 0,46 minus 0,15 V. That is what we have at equilibrium. All right, and we are almost done with the table. We have now that at equilibrium we have, obvious, the initial amount minus the change, how much is change. So this one will give you the final answer there. Now, how do we get equilibrium? We go to the formula here. So concentration is equal to number of mole at equilibrium divided by volume. What is the number of mole at equilibrium? This amount here, 0,46 minus 0,15 V divided by V. And we have everything now in order to substitute in the Kc expression. So let's go to the Kc expression. All right, Kc is equal to the concentration of product. It is here, so I'm not going to rewrite it. Ax3 to the power 2, concentration of the product is 0,1 to the power 2 divided by the concentration of the reactant, 0,46 minus 0,15 V over V is 0,46 minus 0,15 V divided by V to the power 3. To the power 3. And this is the Kc expression. Now, the Kc is given to us. It's given. It's given in the question. They said that the Kc at 300 Kelvin, 300 Kelvin is right here in the table, 300 Kelvin. So if you go to the graph, you will have that the Kc is 10 to the minus 3. So it's 10 to the minus 3. So I'm going to write the number here, the value is 10 to the minus 3. And then all is left is mathematics. Now, this maths might be a little bit tricky, however, it's not a big issue. Alright, so this is going to move to the other side, and we're going to have 0,46 minus 0,15 V divided by V to the power 3 equal to 0,1 square divided by 10 to the power minus 3. So we are there. Now let's do step by step. Okay, let's first do 0,1 divided by 10 to the power minus 3. Alright, instead of calculating this here, it's better to go straight into root cubic on both sizes. You go to root cubic in both sizes to eliminate this to the power 3. So this is gone. So what do we have here at the end? Now we have 0, 0,46 minus 0,15v divided by v. This root cubic is gone. Now on this side you can do the calculation in your calculator. My calculator here is a little bit tricky, so I cannot do it. However, the answer is going to be 2,15. Okay, when you do this calculation here, you will get 2,15. Please check the calculations. All right, so now here we have 0,46 minus 0,15v equal to 2,15v. All right, so now we move everything to the other side. So we have 0,46 is equal to 2,15v plus 0,15v. And then when you do this one, we have that 0,46 is equal to 2,3v. So v will be equal to 0,46 divided by 2,3, and this is equal to 0,2 cubic decimeter. This is the final answer. All right, this is the final answer. Now the mark allocation here is kind of tricky. It's very difficult to get this mark allocation. The marks, you can see if you go to the question, the marks are 8 marks. Now there is very difficult to mark this question. You will get 1 mark for this initial. You will get 1 mark for the using of the ratio. You will get 1 mark for this one. So we have in a 1, 2, 3. Then is a 4 for the expression here. 4 for the expression here. 5 for the substitution of this one. 5, 6, 7, and 8 for the final answer. So the total is 8 marks. All right. Now we are done with this one. I hope you understand, and I hope it really helped you. This is not too difficult. I recommend you to try to do it or use it and then maybe do another example using the idea. Okay. Now question 9.2 and last one. And 9.2 said, what effect will an increase in temperature have on the amount of AX3 at equilibrium? All right. Only write increase, decrease, or remain the same. Now we have to go to the graph. You can see that you need to know that if you get a low Kc, that means that you have or you producing more reactant than product. If you get a greater Kc, that means that you're producing more product than reactant. You can see that as you increase in temperature, they said here, as you increase in temperature, an increase in temperature have a decrease in the Kc, and therefore will have a decrease in the product. All right, a decrease in Kc will have a decrease in the product. So the first answer is decrease. Now, how to explain this one? From the graph, you can see that the Kc decreases as temperature increases. So I will probably write that one. And Kc decreases as temperature increases. That is the first thing I'll write. When the Kc decreases, more reactant are formed. I will write that one. When the Kc decreases, more reactants are formed. All right. Therefore, if you have more reactant form, the reverse reaction is favored. Is favors. and therefore the reverse reaction is exothermic. Remember, a decrease in if you increase in temperature, that will favor the endothermic reaction, and if you increase the temperature, the reverse reaction is favored, therefore that one is exothermic. And then the forward is endothermic. All right, so that is the answer for this question. It's not difficult, it's not a big issue. Now the marks here in this explanation are obvious. 1 mark for saying that decreases, 1 mark for saying the Kc decreases, temperature increases, and then the other one for explaining in terms of exothermic or endothermic. This is 3 marks this question, a total of 11. So I hope it helped. I don't see a big problem with this table. However, Lena struggles a lot. Okay, use it as an example. It will help. Next time we'll go to question 1. It might be a long to explain step by step how to get the answers. Thank you very much. I'll see you next time.